Okay, so you ready for some math? Yeah, right. Stifle your enthusiasm. Okay, again, my name is Betsy, and I work for a company called Netutive. Netutive is about a 12-year-old company, and we really have two lines of business. First is a sort of a legacy business. Our first product was an anomaly detection engine for use in data centers. And recently, we started offering analytics and monitoring in the DevOps, SaaS world. So what I'm going to talk about today, of course, is why analytics fail. And first, though, I think I should add a word have a word from our sponsors. The sponsors would be our customers. While we brought software and math and analytics to the table, customers brought really deep domain knowledge, a sense of adventure, a willingness to collaborate, and of course lots and lots of data. So much of what I'm going to be talking today about is our experience with both sets of customers, the DevOps customers as well as the legacy on-premises customers. But the stories you are about to hear are true, and the names have been changed to protect the innocent. So, first of all, if you look at, I've been quoting an analyst, sort of like Michael did this morning, I guess. This is an analyst picture that maybe you've seen before. It's called the Gartner Hype Cycle. And when you look at DevOps, I'd say it's probably here. It may be a little bit lower, it may be a little bit higher, but basically everybody believes in the potential of DevOps, and there's a lot of excitement around it, and it's relatively early in its adoption cycle. Actually, I'm sort of jealous, because if you look at the analytics for DevOps hype cycle, we're probably more like here. We're probably, back at around 2000 is when analytics and big data were first introduced, and everybody had high hopes for it. And in the case of DevOps, I think basically there's a lot of disappointment around analytics for a number of reasons, and that's why this talk is called Why Analytics Fail. What I think is that it's a bad rap, that analytics should really be here, and so that's what I want to talk about today, is why it's not here and how we can get it to be there, maybe. So, first of all, why do you have analytics at all in DevOps? Well, one of the main reasons, it may not be the only reason, but a huge reason is to find problems. So what can happen when you're looking for problems? Well, you can have success or you can have failure. In the case of success, you have true positives and true negatives. I'll go into that. And in the case of failure, you have false positives and false negatives. So let's first look at success, which is not really what we're going to be talking about much today, to be honest. But in the case of a true positive, what that means is that if you have a sick system or you have a problem, then you get an alarm. That's information you want. A true negative is when everything's silent and everything's okay. If you look at the other side of the coin, which is failure, what you have are true positives. This is false positives. I misspoke. False positives. And what happens in this case is you get the crying wolf situation, where you get inundated with alarms and they're not actionable. They're annoyance more than anything else. And that's a serious failure, and people see that, of course, a lot. The other case, which is actually worse, at least in my experience, the customers are maddest when we miss something that we should have gotten. That's called a false negative, meaning everything's okay, everything's not okay, but my head's in the sand. Okay, now, one way that you can measure the success of analytics is to look at something called the signal-to-noise ratio. And what that is a ratio, and it's the number of true positives that you're seeing, which is what the information that you want. When there's a real thing wrong, you get an alarm. Divided by the false positives. That's the noise, the stuff that you don't want to know. So it's the ratio of wanted information over unwanted information. So what can we do to essentially make the noise ratio, the signal to noise ratio, as high as possible? And what I want to do is talk about really three things. The first is the data that you need to do it. The second is the analytics, which is the math and the algorithms and the models and all that. And then the third is context. So let's take them one at a time. First, with respect to data. Three kinds of data that you typically find in a data center that are available to you from your sensor networks are metrics, attributes, and collections. A metric is probably the most fundamental data structure that you find in a monitoring system. And what that is, of course, is a set of time-stamped and sequenced observations that you get over time. And you may get one every second, you may get one every minute, you may get one every hour, whatever it is. But it's a string of values, and it's easily represented on a dashboard. The thing that's interesting about metrics is they can be long. For example, let's suppose that we're working with a retail chain, and they want to know about the differences between Black Fridays for years. Okay, that's years of data that you may need to keep. So the metric could be really long. The other case about metrics that's interesting is that they can really be plentiful. In a small data set, data center, you can have hundreds of them. In a large data center, you can have millions of them. So this is where the big data really comes in. Second class is attributes, and there's two kinds. This is the sort of standard attribute. It's one that never changes. It's maybe the host name. Maybe that never changes. It could be the units of measure for the metric. Is it gigabytes, or is it milliseconds, or is it number of requests? That doesn't change. The interesting one is the one that changes, and SCD stands for a slowly changing dimension. It's a term that comes from the business intelligence world, but the idea is that this is something that doesn't change as fast as a time series or a metric, but it does change, so it's not a static attribute. And what you find that plentifully in elastic computing, where effectively you're shrinking and growing your infrastructure to meet demand, or in a software-defined data center where you're configuring things and the configuration slowly changes. These are really important attributes, and they can make a huge difference in the accuracy of your alarming. Finally, last type of data is collections. This is something that's surprisingly absent in a lot of solutions that I've seen. It's something that can be taken advantage of for analytics that I think is sort of underutilized at the moment. But the idea is you form collections of time series typically, and the criteria for defining that collection is maybe that it's an entity. It's an element is what I call it. But an element is something like maybe a server or an operating system. If it's an operating system, you might have time series that are context switches per second, CPU utilization, things like that. So you can find groups of time series based on that criterion. You can also do it based on containment. You have a load balanced cluster, how many nodes are in it? Or in the case of networking, connections. In the case of transactions, sequences of transactions. So these are all ways to sort of group time series. So those are the three kinds of data that you can have, and those data all fuel the calculation of analytics. So what kind of analytics can you have? Well, you can have deterministic analytics, and you can have statistical analytics, among others. We'll talk about some samples of these right now. So deterministic analytics, they can either succeed or they can fail. I think they fail a lot, and unfortunately because of that, and because of the fact that they're the current state of the art in DevOps, analytics are getting a bad rap. They make too much noise or they miss things. Let's look at some samples and why they fail. And also, also why they succeed. Okay, so there's three types we'll look at: dashboards, static thresholds, and transformations. Maybe all of those of you who use monitoring tools, you're probably used to seeing some of these kinds of things. So first of all, with respect to visualization, it's a terrific way for somebody to quickly get a lot of information. The human brain is very good at pattern recognition, and I don't know any DevOps, particularly ops people or even application, dev people, so to speak, that don't rely a lot on dashboards. However, that's the success part. The failure part is they don't scale. The more metrics you have, the bigger the wall, and the more likely you're going to miss something. That happens a lot. So as the number of metrics grows, the probability of a missed alarm increases also, probably exponentially. Okay, moving on to static thresholds. The good news is that they're intuitive. They're very easy to implement from a product perspective. And they're intuitive from the standpoint that somebody can just, pick a value, and lo and behold, whenever it goes over it, you can get an alarm. Of course, that can be dangerous, but it's a great start. But moving on, they can be hard to set. For example, if you set it too low, then you get the crying wolf problem. You get a bunch of spurious alarms that are totally inactionable and basically something you want to ignore. The other case is that you set it too high, in which case you miss something that's important. Or you can set it just right. And all of this requires a lot of thought. And if you have to do this for a lot of metrics, then that gets to be a problem when it comes to scale. Another problem with static thresholds is there's shapes that metrics can take on that are not really conducive to thresholding. A lot of open source agents, for example, are configured to send data cumulatively, not what's changed every individual interval, but just a sum, adding to a sum. And that creates a monotonically increasing line. I mean, you can't set a threshold for that. However, you can potentially transform it into something that is making the alarm a little bit, or the anomaly, I guess, a little bit more obvious. But if you don't do that, then of course you end up with your head in the sand. Another shape that's a problem for static thresholds is a sudden change. In this case, if you've said that the upper above the threshold is bad, then you get a bunch of noise and you really can't win. If you said lower was bad, then you get noise again. So let's look a little bit at the transformations, which is the next sort of technique that seems to be widely available these days. Is you can basically take a raw metric coming in and you can apply a function to it. A really common one is a delta function. That's where you're taking the most recent observation and subtracting the one before. So you're seeing, instead of seeing something monotonically increasing, like in this case, if you apply a delta function, then you can get something that exposes the problem a little bit more readily. What's interesting, and something that's less often seen, is the notion of creating a histogram. It's called a frequency histogram. And the idea here is you just take ranges of values that you've observed in the metrics. In this case, the values seem to go from about 80 to 200. And you take ranges and count how many observations were in each interval in that range, say a 5-point wide interval. Okay? What you get with the counts is you get a bar graph showing the counts. And the higher the count, of course, the more common that value is. So what you can do with this is look for the rare values. That's the places where the bar is short. And this may be a way, potentially, to replace static thresholds, where you can discover the threshold just by using a frequency histogram, and all that could be automated, which is nice. Another really problematic form is the seasonal form. And by season, I don't mean Christmas, New Year's, and Thanksgiving. What I mean is a sort of predictable and repetitive pattern that occurs in the metric. This happens a lot in the retail industry. You have nothing going on at night, and you have a lot going on during the day. But let's suppose that during the middle of the day, you see an observation that's shown by that red dot. It's perfectly fine observation at night, but it's not a good observation during the day. And it's very difficult for an analytic, especially a deterministic analytic, to figure that out. So what happens when you try to do a transformation into a frequency histogram, which works in a lot of cases, it doesn't work so well here. The reason for that is because the red dot is a common value. It's just occurring at the wrong time. Okay? So let's move on to some statistical analytics. and look at where they succeed and where they fail. I would say that this is probably where the state of the art is heading because they've been very successful in other applications, so there's no reason to believe it won't be equally successful in DevOps. There is one caveat, however, and with things like elastic computing and software-defined data centers, the unifying assumption here that what's passed is prologue, that's what statistics relies on. It uses what you've observed in the past to decide what you expect in the future. So you have to be somewhat creative, I guess, in using the statistical kinds of analytics. But let's look at a couple of them. There's two that we're going to look at. One is called correlation. That's a correlation model. And the other is called machine learning. And both of these are multivariate. Or they don't have to be. I guess I have one example that's univariate. But both of these rely on statistics. And so what I'll talk first about is correlation. Let me just mention about correlation is that correlation is typically applied for two metrics at a time to see how coordinated their behavior is. It's a measurement. And the measurement can range from -1 to 1. If it's -1, then whenever one metric goes up, the other metric goes the other way. Okay, and you get a slope, actually, if you do a scatter plot, you get a slope that's negative. In the other case, the other extreme, if one metric goes up and the other metric always follows it and goes up, and they both do this sort of in a consistent way with a consistent amount, then you get a very high correlation coefficient. So let me just elaborate on that a little. The importance of correlation for detecting problems is this. If you take a scatter plot, which is basically each one of these x's, for example, is representing one point in the scatter plot, and the first coordinate is the value of in this case, say, requests per second, and the second value in the pair that's being plotted here is the revenues per second. So at any point in time, you have two measurements, and you plot that on here. And what you can see here is that typically, as requests per second go up, revenue goes up. Nice trend. So, and what it does is it gives you the ability to make a prediction. You can say, okay, if I know I'm having this many requests per second, then I know that I should expect roughly this many requests per second. And what I've done to get to that point is to fit a line. Maybe you remember from your high school math, regression analysis, linear regression. Does it bring back fond memories? Yes, I didn't think so. Okay. Anyway, if you do that, you can just, there are packages that do it. So you can get sort of a band of normalcy, what you would expect if the requests were as represented in this vertical line. And furthermore, you can add a level of confidence. You can say, well, I want to be 80% confidence, in which case you get a pretty wide band. But if you want to be 99% confident, then the band's going to be smaller. So in this way, correlation can help you identify something that's wrong. Because if you get a particular known value of requests per second, and you get something for revenue per second that's significantly lower, well, that's not good news. That's a good candidate for some further investigation. So because this is about analytics and because this is about math, I figured it was really important to put at least a few Greek letters up. So here they are. But probably more importantly, this is a very simple equation. It's something that's computationally trivial for a computer to do. So what that tells you, or you can just take it from me, trust me, that basically doing this in real time is not a real big deal. It's something you can do with, on second data, 1 minute data, and here's how you might discover something. You compute the correlation coefficient, which is called the Pearson product moment coefficient of correlation. You can look it up on Wikipedia. But let's take a look at how that could help you discover a problem. Here's two correlated metrics. When one goes up, the other one goes up. And the amount of upness and downness is pretty consistent across all the observations. So its coefficient of correlation is around 0.91, which is close to a perfect positive correlation. That's cool. So now let's suppose one of the metrics kind of goes sideways. Something weird happens. Then the coefficient of correlation drops dramatically. That's a good thing to be able to discover. So that's a success. But like everything, there's the other side of the coin. Here's where this sort of thing could fail. And the way it could fail is, let's suppose that you had a problem here in the middle of the day where both metrics plunged, which quite often is the case. The correlation stays perfect. 0.92, it even went up. So in this case, if you were just using correlation to detect the problem, you'd end up missing it. And just to sort of elucidate, talk a little bit more about this, I guess. The reason you missed it is not because correlation is a bad measure. It's because what you want to know about is not necessarily the interaction of these two things in this particular case, or how well they're coordinated. What you want to know is the value, which is where probably a static threshold would be better. Okay, maybe not perfect, but better. Because all of the x's here in the red area, those are the x's that happened when it dropped. And it dropped to an unhappily low value for revenue, which is always of interest. Okay, so that's correlation. Let's look at standard statistical machine learning. This is increasingly popular. There's increasingly available, open source libraries for doing this. The tricky part is doing it in real time, but let's talk about just how it works first. First, you have a learning phase. So you feed metrics into this black box that's a learning engine. It has all kinds of heavy math, time-consuming algorithms that suffer from all kinds of maladies like overfitting and dividing by zero and all kinds of horrible things. It's complicated. But you don't need to know about it. It's just a black box. So you feed it in, and what you get out are parameters that allow you to detect problems or anomalies or deviations from what you would expect given the past, right? So now that you have the parameters, you go into phase 2, which is the detection phase. And here you're feeding more metrics in over time. And the parameters now are helping this black box determine when there's a problem of some sort. And a third phase is possible with inline machine learning, adaptive machine learning, where essentially what you're doing is taking the metrics in, the parameters in, you're getting anomalies out, or the potential problems out, but you're also getting adjustments to adjust to what might be a changing situation, which can be helpful with the sort of dynamic computing environment that DevOps is typically dealing with. Now, all of this complexity can be relatively easily visualized. So this is is one way to visualize the results of what the learning engine is telling you. And it's actually pretty easy and pretty natural or intuitive to interpret. What you have in the first case is you have a black line, and that's the raw values that you're observing, right? Then what you have are these bands. And the first band, the widest band, is the green one. And that is that's the result of a learning model that involves only one metric. So it's looking at one metric over time. The model is determining what a standard deviation is for that, which is sort of a measure of variability. And then what it does is it defines bands of what it expects, and the width of the band is a function of what kind of confidence you want to have that when it goes outside of the band, you have a problem. And that's all tunable, of course. What's interesting is there are other types of machine learning algorithms that use collections of time series. So you could have a collection of time series that measures a whole path, let's say, of a transaction from the user all the way through and back. Okay? You put those metrics together in a collection, and now you have a lot more information, so you get a much better estimate of what you think this metric should, what the variability of the metric should be, and what the normal band of normalcy would be. And the reason for that is basically you have a lot more information. Not only do you have all the metrics that are in the collection, but you have all their interactions, how one influences the behavior of the other. And then what the outcome of the model is given that I know all the values of all but one metric, I can predict what that nth metric sort of, where it should be. Here's just a graph of learning. This is a univariate learning model, and what you can see is the band is really wide to begin with. And then what happens over time is it learns that this guy doesn't vary very much. He has a few humps in him, and you can see that the green band follows that. But you can also see that there's in a little tiny red dot, the metric zigged when it should have zagged, and it can catch that because it's outside of the band. Here's a much more complicated one. This is a pattern. This is from retail store data. It's actually credit card authorization numbers, counts of credit card authorizations. And what you can see is there is a couple of cases where during the day, the black line went to nothing. So it can catch this kind of contextual deviation. It can detect that it shouldn't be zero during the day. And this is all just through machine learning. So all those 3 points are outside of both bands. Here's another case which is pretty interesting. This is a case where you have machine learning where the metric is CPU utilization. And let's just say, for the sake of interest, that we're an AWS customer and we moved an EC2 from being an M4 large to a T2 small. In the case of the M4 large, the CPU utilization is a lot lower. So I had excess capacity that I didn't need, so why pay for it? I think a M4 large is around 12 cents an hour and a T2 small is around 2 cents an hour. So I'm saving a lot of money by doing that. And what happened is that the CPU utilization jumped as soon as the T2 small came online. And as you can see in the learning engine, it's not perfect because you get some alarms. And these are reasonably characterized, as false alarms. But then pretty quickly it adjusts, and now it's detected the new normal, which is pretty impressive. However, like any yin, there's a yang. Let's suppose that instead of measuring CPU utilization, we were measuring response time. Okay, it's not a new normal now. It's bad news, and it's bad news that's lasted for a long, long time. We're not meeting our SLAs, and meanwhile, this algorithm is thinking everything's just fine. That's the worst kind of problem. That's the head in the sand problem. So nothing's perfect. Okay. Bottom line is, while math may be the queen of the sciences, and that may be impressive, but it's not enough. So what you need to do is you need to add context. Adding context is absolutely critical. And how do you do that? Well, the first thing is you need to have, first of all, a broad repertoire of analytics to apply to your problem, so you have the right analytic for the right thing you're trying to find. And the next thing is to use the right tool once you've chosen it. Second thing is you've got to somehow think of analytics as not really math, but a workflow. It starts with data coming in. You detect problems using the models and the math and the algorithms and all that. That becomes results, and then there has to be something that's a buffer between the pure math and actually enunciating a problem or waking somebody up at 3 a.m. Unfortunately, my time is up, so I can't tell you about that mysterious context bubble. So the big takeaways. The best analytics include not only math, but also sort of human knowledge, human domain knowledge, and that can be baked into a workflow somehow. Maybe that'll be my next talk. And most importantly, success consists of going from failure to failure without losing enthusiasm. Okay, that's it. Thank you.